are there any stars lacking neutron capture elements? Now, at first, I just want to focus on the detectability of heavy elements. For that, we can use the resonance lines of ionized strontium and barium. These are the two heavy elements that are the most readily detectable at low metallicity. So using all of the abundance data available in the literature from the last 20 years or so, I compiled a sample of about 700 stars in the field and about 70 stars in dwarf galaxies in the local group. And these come from both the classical dwarf spheroidals and the ultra-faint dwarf galaxies. Here's one way to visualize the result. So this figure shows the barium to hydrogen ratio as a function of the strontium to hydrogen ratio. Both of these ratios are logarithmic, and they're both relative to the solar ratio. So you'd find the sun here at 0, 0. The red points and the blue circles, of course, mark detections, and then those arrows mark upper limits derived from non-detections. Check out the lower left corner of this plot. That's where things get really interesting. There are some upper limits here, but there are also a handful of detections in the very same region of the diagram. And the upper limits are not substantially lower than the lowest detections known at present. So in other words, we have not detected any floor in these ratios below which all we have are upper limits. So are there any stars lacking neutron capture elements? Well, maybe, but the observational data here suggests that such stars are not found, or they're extremely rare in existing samples. Here's another way you can ask the question. Are there any environments lacking neutron capture elements? Right? There were some upper limits in that last figure. Are those stars spatially or kinematically correlated, or are they somehow related to one another? Well, neutron capture elements have been found in all bulge stars, disk stars, globular clusters, and stellar streams that have been studied. The abundances of the heavy elements are extremely low in some of the ultra-faint dwarf galaxies. But with one exception, at least some stars in every single galaxy that has been studied, so from the luminous ones like Fornax and Sculptor, down to the low luminosity ones, think Hercules, Segway 1, Segway 2. All of these show the presence of strontium and barium. Now we can say this another way, in that each present-day galaxy, again with only one exception, each present-day galaxy is comprised of stars from one or more mini-halos that experienced at least one neutron capture enrichment event. So neutron capture elements are rarely, if ever, just missing from the star-forming environments that built up the Milky Way and its neighbors. And I think that Alex G. has also articulated a compelling case for this in the context of the ultra-faint dwarf galaxies. Here's another way you can attack the problem. A 10-year observing campaign at the Magellan telescopes has produced exactly the data set that you'd want to improve the observations. And our results reveal that once you go to stars cooler than about 5,400 Kelvin, so these are the stars where the absorption lines are strongest for a given composition. Once you go to the coolest stars, strontium and barium can be detected in every single one of them. Every one. So when the observations are of sufficient quality to detect weak lines in cool stars, they do. Here's another approach to the problem. This is one that highlights a piece of cognitive dissonance that I see sometimes. So this concerns the class of carbon-enhanced metal-poor stars with no enhancement of neutron capture elements. So these stars are typically enhanced in elements like carbon, nitrogen, oxygen, magnesium, at least relative to their iron content. The heaviest elements in these stars, things like strontium, barium, and europium, these are also not enhanced. Now, these stars tend to be preferentially found in remote, chemically pristine environments. And today it is generally accepted that these carbon-enhanced but ridiculously iron-poor stars, that they probably form from the metals produced by just a single zero metallicity star. And this is where I observe the cognitive dissonance. The CEMP no stars do contain neutron-capture elements. Right? Sometimes we slip into thinking that this no means none. Sometimes we ask the question about what kind of star or supernova could have produced the light elements in these stars, but without also asking whether or not it could have produced the heavy ones. Here's an example. This figure shows a piece of the spectrum around the magnesium B triplet. In the Sun, a normal metal-poor star, and one of the ridiculously iron-poor stars, a second-generation star. As you can see, those lines do get progressively weaker as you go to lower metallicity from top to bottom, but they are still detectable. And you would infer from this that magnesium was produced by that first-generation star. The figure on the right shows the same three stars, but now a piece of the spectrum around the strontium line. Again, as you can see, that line does get progressively weaker at lower metallicity, but it is still detectable. And by the same logic, you would also infer that strontium was produced by that first-generation star. When we look at a slightly more iron-rich regime, here's what we find. So these are just plots of log of the abundance as a function of atomic number. Each panel shows a different star, and these are four of the more well-known and well-studied members of the CEMP no class of stars. Now, even in these stars, there are still clear consensus detections of strontium and barium. Other elements, like europium, could also be present, but they would still be below our detection threshold. When we look at other extremely metal-poor carbon-enhanced stars, we find the same result. You always see strontium, and you nearly always see barium. So we've established that neutron capture elements are present. Now we can ask questions about the nucleosynthesis. But it is really difficult to say what kind of neutron capture process is responsible when you only have one ratio of two elements, right? It's really difficult to exclude different models. And so you don't have much confidence in anything just because it happens to fit that one ratio. Well, in a few cases, we can detect significant numbers of other heavy elements like europium. And once you have a few more elements, then the kind of nucleosynthesis process becomes more clear. So you can see that in these plots. Again, just log of the abundance as a function of atomic number. In the few cases where we can detect significant numbers of other heavy elements, the abundance patterns are indicative of our process nucleosynthesis. That's what's shown by the red and the orange lines. So we're left with a situation where one or both of the following statements must be true. One or both must be true. Maybe our assumptions about how many previous generations of stars contribute metals to the CEMP no stars, maybe those assumptions are incorrect. Maybe more than one generation of star did. Or maybe the R process operated in some of the first stars. For the first possibility, that's not typically how we think of these stars. We think of the CEMP no stars as second-generation stars. And for the second one, the problem is that existing models don't predict that, right? So my challenge, my question to the supernova and nucleosynthesis experts in the audience is this: is there any theoretical way to produce an R process? Even if it is a weak R process, that's fine, as long as it still goes through the rare earth domain. Is there any way to do this in a zero metallicity star? Okay, so I'd like to finish up, switch gears for the last few minutes here, and promote a future facility. Now, this one doesn't appear in the lineup for Friday afternoon, but it is critical to understanding the nature of the first stars. The science driver here is UV spectroscopy. And I'm not just talking about UV observations of neutron capture elements, although for me, that's still a big part of it. UV spectra enables a 40% increase. A 40% increase in the number of heavy elements you can detect. So in the context of the metal poor stars that we're discussing this week, this figure shows the elements where you need UV spectra to derive reliable abundances, or in many cases, to simply even make a detection. Today, if you want a UV spectrum, there is no choice, right? The Hubble Space Telescope is your only option. Having said that, the two UV spectrographs on HST are operating smoothly, and Hubble's mission has recently been extended until at least 2021. After that, there's something called WSO-UV. This is sponsored by the Russian Federal Space Agency and the Spanish government, and this is scheduled for launch in about 2021 or so. But WSO-UV only has half the collecting area of HST. So it will be difficult to make transformative gains over what we can do today with HST. AURA has commissioned a report to consider the possibility of a 10-meter class UV optical IR telescope in space. They adopted the name HDST. NASA also has a working concept, which they're calling LUVOIR. These are basically the same idea. And the goal is to have a report with strong community support ready for the US 2020 Decadal Survey. Now, this is still 20 years away from launch in the best case scenario, but allow me to describe some of the ways that this would revolutionize the field. Here's one way to visualize this. The red circle here illustrates the region of the Milky Way where HST can get high-resolution UV spectra of red giants. This is today. The blue circle illustrates the region where HDST or LUVOIR could observe. So let that sink in for a minute. This would enable you to take a high-quality UV spectrum of nearly any star whose optical spectrum you can get from the ground today. So let's bring this home in the context of the first stars. Many of you may be familiar with the most iron-poor star known. Right, this is the one discovered by Keller et al., who could only get an upper limit on the iron abundance from lines in the optical. Iron lines in the UV should be much stronger. So last year, I took a spectrum. Even at a V magnitude of 14.7, this star is still way too faint for HST. This is a piece of the spectrum around the strongest iron 2 line. The strongest iron 2 line. And unfortunately, everything you see there is just noise. But with something like HDST or LUVOIR, this would be a simple observation. A UV spectrum of every ultra-metal poor star known would be a simple observation. And when you've got those UV spectra, you can double, if not triple, the number of heavy elements, the number of metals you can detect. And that is how you make serious progress in understanding the IMF and the end states of the first stars and the distribution of the first metals in the proto-Milky Way. In the era after Gaia, after JWST, after W first and Euclid, after the foremost spectroscopic survey, in the era when the high-resolution optical spectrographs on the 30-meter class telescopes are fully operational, and you've finally had 1 or 2 ALMA proposals approved, in the era when the facility for rare isotope beams is humming along, and the results from numerous gravitational wave observatories around the globe have exceeded our wildest imaginations. In that era, if you want to get a UV spectrum, nothing fancy, just a simple UV spectrum, this will be the only game in town. I hope this is something you will join me in supporting when the time comes. Thank you.
Thanks a lot. Do we have comments or declaration of interest for this team?
Yes, well, no surprise, I support your party platform, and indeed, I think something else which is missed by people on the outside looking in that we ought to be at least self-aware of in this community that cares about stellar and nearby galaxy abundances, and that is we have no full-time facility on planet Earth dedicated to measuring abundances. Full-time, large, full-time. So that when the idea comes out in a meeting like this, which is eminently testable, one can't just go to a telescope and write a proposal for which one of or other of the proposals will be selected because this will be measured. So we're not here 4 years from now asking the same question of the people who wrote proposals that didn't get approved. And we're actually in a state right now where we are running against resistance from committees, time allocation committees that don't understand the details we're actually capable of measuring today. So if there's no cosmology in your proposal, what's the point? We can do things with uranium and thorium other than divide them and obtain a limit on the age of the universe, like understand the R process. Good luck getting that through a committee on an 8-meter telescope. So anyway, I just wanted to inject that. I think I said it 5 years, 4 years, 10 years ago, but it's still there.
I'll say it again in 15 or 20.
Yeah, exactly.
Yeah, yeah. Thanks.
Okay, Jackie?
Generally speaking, it is no problem to have a weak R process associated to quark supernova. I think it's already shown by many researchers. But quantitatively, I am not sure. So in the figure, the orange line, which yield did you take?
Those were not yields, those were, so what I was calling weak R process is the star, the pattern in the star that many of us typically associate with that, which is HD 122563. The one for the main was CS228925052. So there's a small sleight of hand there. Those are not theoretical yields from models, those are empirically drawn.
Gabriele?
Just a quick comment. I mean, the problem typically for a weak R process is exactly to produce barium. So if you take, of course, this star as a reference, yeah, you can say that a weak R process can do that, but it's a theoretical issue still. And maybe as an obvious question for myself, why you don't show also the yields for S processing massive rotating stars at low metallicity? They can produce actually both strontium and barium.
They can.
They can, yes.
But my point is that in the few cases where we have more elements to constrain what the model is, it doesn't look like an S process through the rare earth domain.
Yeah, but you showed the main S process. I'm talking about the S process coming from massive velocity. It's completely different, the shape of the S
Fair
process.
enough. But
I will pass to you the line without,
Okay.
then you can add this.
well, there are patterns to try and model to have it reproduce. Yeah. We'll talk.
Okay, so I would thank Ian again and all the speakers.